I think we can't hear you.
Is that good?
Oh, yep, no, we're good. Okay, fantastic. So up next we have Jim Halverson talking about building quantum field theories out of neurons.
All right. Hello, everyone. Thanks for the invitation to speak here, to the organizers. It's been a wonderful conference so far. It's nice that we're sort of in the fourth iteration, and it seems that we all have broader and broader interests in this area over time, which is really exciting. So I'm going to speak on some work today that appeared recently and is inspired by work with my students, and also works with Sergei Gukov and Matt Schwartz. If possible, I'm going to change the geometry of this window a little bit. Hopefully that still looks okay. Good. And I think hopefully the title sort of makes clear what I'm after, and I'll present some first results in this direction. So first of all, thanks to my wonderful students for the collaborations we've had on related works, some of which I'll talk about today. Anandita is applying for postdocs next year, so I've got her for an extra year. And Keegan has realized that there are other green pastures other than academia, and is going to be targeting ML labs to start in fall of 2022. So if you're in a machine learning lab and you're interested in this work, definitely look for Keegan's application and even get in touch with him. So there are many ways to connect with the physics and machine learning interface these days. Here are three of them. One is this NSF Institute that I am happy to be a part of. The NSF Institute for Artificial Intelligence and Fundamental Interactions. A point that I want to emphasize, because I think there are many students in the audience, is that we are having a summer school in 2022 that will emphasize all of the different aspects of research at IFI. And second of all, there's Physics Meets ML, which is a virtual seminar series that some friends and I, many of whom are in the audience, have been organizing for some time now. This is bi-weekly, and this has been a great way to connect at this interface during the pandemic. And if you have any questions about the sorts of things that I'm talking about today, or more generally, sort of in this string theory, and well, feel free to reach out if you're interested in these particular works. This is our official IFI slide that emphasizes some of the things that our institute is about. Really, I'd just like to present it in case you're interested afterwards about ways to connect to the institute. We have a Twitter account, we have a website, you can contact management, and we're doing a lot of different things at this interface, and it's very exciting. So as we've just heard a little bit about, there is some work about using field theory-esque ideas for machine learning. Dan didn't really couch his talk in that way, but that's one of the ways of thinking about what he's doing. And here are some of the works in this area that have been inspirational for me over the last couple of years. And there's a growing literature in this area of people doing various different things, and hopefully the titles make it clear what people are doing. But one of the great things is at this conference we get to hear a number of different aspects of this direction, and I think that that's really exciting, and I'm excited for these talks, and Dan's talk was great. So I'm going to try to do something different here. Instead of trying to take physics techniques and apply them to machine learning, I'm going to try to take neural network and machine learning techniques and apply them to QFT. And in particular, some of the questions that we're going to be interested in are, what if we're going to have a neural network approach to field theory, what takes the place of an action? Are there design principles? Normally in field theory, there are certain types of things that we want to be true. And so if you're going to have a neural network approach to those things, what are the design principles? And in particular, how do we think about symmetry in that context? Anandita will give a whole talk on symmetry in that context, which I refer you to. And finally, if there's going to be interactions in this setup, if there's going to be interactions in this setup, where are they coming from? And finally, one of the central questions, the neural networks that we have today are going to engineer ensembles of Euclidean fields. They're Euclidean field theories or statistical field theories. But in that context, there's a question, when can we Wick rotate Lorentzian signature and get a quantum field theory defined by the neural networks? So these are some of the things that I'm interested in that were discussed in this recent letter that I put out, and I'd like to tell you about them today. So first, I'm going to tell you about building quantum fields out of neurons. That's sort of the essence of the setup. I'm then going to tell you how we get interactions in that sort of setup. The basic statement is that we get Gaussian theories due to the central limit theorem in this context. So if you want to turn on interactions, if you want to have non-Gaussianities, you need to break some assumption of the central limit theorem. And there's at least two ways to do that. Then we're going to talk a little bit about engineering symmetries, and in particular, I will be after Euclidean invariance. I'm interested in Euclidean invariance because if we are going to be able to Wick rotate to Lorentzian signature, this is the symmetry that is relevant for obtaining a Lorentzian field theory. I'm then going to introduce a notion of neural network quantum field theories and tell you what that might mean in the context of certain axioms that are out there for field theory. And I'll give you a couple of examples. So in particular, I'll give you a Gaussian neural network quantum field theory that you know and love. And I'll also give an example that is not a quantum field theory, but exhibits large N duality. So building quantum fields out of neurons, this is the first part of the talk. This is the essential idea. The basic idea is that I'm going to consider some field phi that is a sum of n generally non-Gaussian neurons, hi of x. And think of this as some post-activation in some deep network that I then take a linear layer to construct a real scalar out of. So these AIs are parameters. And the HIs have parameters in them as well that I'll call theta h, so that the full set of parameters is theta, which is the A's and the theta h's together. Now, just like in generally for neural networks, these parameters will be drawn from some distribution. This is part of the defining data of a neural network. And in particular, I'm going to emphasize here, first of all, that these neurons are generally non-Gaussian. I will take them to be identically distributed, but I will not necessarily take them to be independently distributed. And an interesting thing here is that a priori, without some work, we don't know an action for the fields or for the neurons. There's no S of phi or S of h that is totally obvious in this game. And so in particular, we can construct these functions drawn from some distribution in principle, but we don't a priori know what that distribution is. Instead, we can just sample these and construct these based on the knowledge of the architecture and the parameters and the distributions that they're drawn from. So if you'd like, the randomness of the fields in this setup is not coming from the action, it's coming from the construction. If you'd like, the theory is defined by an architecture, not necessarily a Lagrangian. And there's some—
Sorry to interrupt you, Jim. Can you say again where the thetas enter into your expression for the field?
Yeah, sorry. These thetas are collectively these A's here. And then these H's, Eva, could be some deep network itself, which has its other parameters, theta H.
Okay, so the theta H's are in H. That makes sense. Sorry.
That's
thank you.
Right. Yeah, thank you. Yeah. So this is the setup. So there's this beautiful work of Williams from 1996, which is in the Gaussian process setup where these sorts of things were computed. So this is how one way that we compute in my group. I think this is how Dan and company compute as well. It's how Show computes. The basic setup is in this way that we're constructing fields from neurons, where the setup is defined by an architecture, not necessarily Lagrangian. One of the basic points is that you can get field and neuron correlators just via parameter space expressions directly. Okay, so this is just an expression for an expectation value of products of fields. But it's integrated against the parameter distribution rather than against a Euclidean action, as we normally would in quantum field theory. So these are exact expressions in parameter space. They don't require knowledge of the action associated with the field or the action associated with the neurons. Sometimes you can evaluate these exactly, just like in field theory. Just because you can write down the integral that you're interested in doesn't mean that you can actually evaluate it. But sometimes you can. And so in particular, whether or not you can evaluate it exactly, you can study and utilize this in various different ways. For example, you can study and utilize this to study symmetries, even if you can't do the integral. And that's what Anandita is going to talk about. So in particular, in this setup, you can just write down an expression for the two-point function. Here's what it is. So it's determined that the two-point function for the fields themselves is determined by the diagonal part of the neuron two-point function right here. This is in Williams' work. But more generally, the field correlators are functions of the neuron correlators themselves. And in particular, I would note a technical point that the n scaling was chosen wisely so that this thing doesn't diverge. And second of all, that on the right-hand side, we don't have a sum over I, and this is coming from the fact that the neurons are identically distributed. But those are some technical points. So we have correlation functions, and we can compute them in parameter space. So in this setup, I'll mention free theories in a second. Generally speaking, I want to ask, how is it that interactions get turned on in this setup? And the Gaussianity of the theory arises via the central limit theorem. So if you need non-Gaussianities because you want interactions, you need to break the central limit theorem. So just a reminder of something that is ubiquitous in the machine learning literature is what's called the neural network Gaussian process correspondence. In this setup, the basic statement is that when you have fields built out of neurons in this way, then those fields are drawn from a Gaussian distribution on functions by the central limit theorem when you have an infinite sum, so you're in the n goes to infinity limit, and the sum is of independent random variables. Okay. And I emphasize again that this does not require Gaussian neurons H. The H's can be non-Gaussian, and nevertheless you get a Gaussian theory for phi by the central limit theorem. So this goes by the name neural network Gaussian process. These are very, very general in various neural network architectures, and we're going to be focusing on doing physics with these sorts of ideas. This is a slide that I have in sort of my ML-oriented talks with many references about just how general these things are. But I think Greg's in the audience, and he's someone that has established this to a great degree. But what I'm interested in here is interactions from breaking the central limit theorem. So the Gaussianity of the field theories in this context comes from the central limit theorem. We're going to study the connected 4-point function. And it turns out that there's two types of terms in the 4-point function. One is this IN4 that I call it, and the other is this IIB4. This IN4 takes this term. These little h's are just particular neuron correlators. So the correlation function, connected 4-point function for the fields can be written in terms of different terms with different neuron correlators. So this type of term, IN4, note that this vanishes in the n goes to infinity limit. So this is one type of interaction that gets turned on by introducing finite n effects in these neural networks. But there's a second that hasn't been emphasized to my knowledge previously in the literature, which is that you can also break the independence assumption of the central limit theorem. So there are other types of terms that arise. This whole calculation is like a little half-page or one-page calculation. And what I would point out about these types of terms is that in the limit that the neurons are independent, these 4-point correlators of this form factorize into correlators of this form. And the reason that this is relevant is because in the independence limit, when the neurons are independently distributed, these terms cancel those terms. So if you'd like, this gives an organizing principle for understanding the interactions in these setup. There are those interactions that arise due to finite n corrections, and then there are those interactions that arise from breaking the independence of the neurons. Okay. And there's other things to say about parametric control, but I'll leave that. Another thing that you're interested in if you're trying to do quantum field theory with neural networks is engineering symmetries. We'll hear a whole talk on this next, but I want to emphasize the particular role that Euclidean invariance might play. So the basic idea of symmetries in this context is to recall, first of all, that we can compute the correlators in parameter space. And then if we can demonstrate the symmetries via the parameter space study of correlators, then we can establish the existence of symmetries of the whole system. So in particular, under certain types of transformations, the correlation functions can be demonstrated to be invariant, which tells you that your system has a symmetry. There's a simple example of a Z2 symmetry, and the Z2 symmetry arises from our original choice that the odd moments of this A distribution are 0, and that ensures that all of the odd correlators are 0, which is correlating with the existence of a 2-point symmetry, a Z2 symmetry. So more generally, the existence or non-existence of symmetries arises from the properties of the parameter measures and the densities and can be shown explicitly. And we'll hear this whole talk on this next. In the interest of time, I'd like to be a little brief on this slide. So we could have the case where the neuron is constructed out of some complicated layer that acts on some input layer. And it turns out that the symmetries can be inherited. The symmetries of some input layer can be inherited via some complicated transformation. The neuron can inherit the symmetries of the input layer if the field and neuron ensembles satisfy a particular decoupling of parameters. So that's something that can be engineered. My point is I'm going to play a lot with this input layer and its symmetries, which are going to engineer space-time symmetries. But you can prepend this to a deep neural network and inherit and have the neuron, the complicated neuron, inherit the symmetries if a particular condition is satisfied. So Euclidean invariance is what we're after, so that we can get Lorentz invariance after an analytic continuation. At left, we have a family of Euclidean invariant input layer architectures. So if you have input layer neurons of this form, drawn from these particular distributions, it turns out that that ensemble of functions, as measured by its correlation functions, are invariant under Euclidean symmetry. So I have the result for translation invariance here. The basic statement is that the correlation functions of these input neurons factorizes in a way that you can evaluate the expectation value over these shift parameters before you evaluate the expectation value over these B parameters here. And it demonstrates the basic type of result that you have here, that what we're doing is we're doing a shift of the input by some vector dj, and we can reabsorb that into parameters c tilde. And if the expectation value is invariant under that parameter redefinition, then what you have is invariant correlators. So that's the basic mechanism that we'll hear an entire talk on next. But here it establishes translation invariance for neurons of this type. And in particular, you can also show that you get SOD invariance of this input neuron ensemble if this function f and this distribution p themselves allow for invariance. So there's some choices, but it can be done, and we can get Euclidean invariance. Okay. So given Euclidean invariance, you might ask, under what circumstances can I really get a proper neural network quantum field theory? So far, everything that we've done in this talk is build ensembles of Euclidean fields from neural networks. And I just explained how you can get Euclidean invariant neurons and Euclidean invariant field theories from setups like that. And so you might ask, when is it that I can take that Euclidean field theory and analytically continue it, do a Wick rotation, such that the result is a unitary Lorentzian quantum field theory? If you'd like, to the extent that this can be done in any degree of generality, this gives a sort of a neural network construction of a proper quantum field theory. So this definition of a neural network quantum field theory, that it's the Wick rotation of a unitary Lorentzian quantum field theory, sort of begs the question, when is a Euclidean theory the Wick rotation of a Lorentzian quantum field theory? And this is one of the subjects that is studied in axiomatic quantum field theory. So there's this famous work of Osterwalder and Schrader from 1972. And you can see from their abstract, which I guess they're going by the axiom that really important results need very, very short abstracts. They established the necessary and sufficient conditions for Euclidean Green's functions to define a unique Whiteman quantum field theory. So the axioms involve temperedness, Euclidean covariance, which we just engineered, reflection positivity, which we'll comment on in a minute, permutation symmetry of switching the inputs, and permutation symmetry of the correlation functions. That's just trivial for neural networks, and cluster decomposition. But the reason that I'm interested in this is because I want to know, if I work hard to engineer a neural network architecture, what are the properties that it needs to satisfy such that it actually defines a quantum field theory? So reflection positivity is something that is perhaps one of the major Osterwalder and Schrader results. The basic statement is that unitarity of the Lorentzian theory is related to something called reflection positivity of the associated Euclidean theory. So in Euclidean, it turns out that the Hermitian adjoint of an operator reflects in Euclidean time. That's sort of a one-line computation given the Heisenberg approach to the operator, the Heisenberg unitary time evolution. And because of that, if I prepare some state psi acting on the vacuum with some number of operators with Euclidean time inserted in this way, the associated bra takes this form. And if I form the bra-ket pair and realize that this needs to be non-negative, what I find is that you can take this acting on this and recognize that it's a particular type of Euclidean Green's function. Yeah. And so what this does is that this yields a constraint called reflection positivity on Euclidean correlators. And so reflection positivity is something that is intimately tied to unitarity of the Lorentzian theory.
You have about 5 minutes left.
Absolutely. I'll get there, I promise. So here I'm going to content myself to check the 2-point condition, which ensures reflection positivity of any Gaussian process, and therefore of neural network Gaussian processes. And in particular, because we're interested in Euclidean invariant theories, which are specifically translation invariant, the condition simplifies a little bit, that the reflection positivity for a translation invariant theory, we first remember that the 2-point function is entirely determined by its power spectrum, by its Fourier transform. And then you can ask, what is the reflection positivity constraint on the power spectrum? So any translation invariant neural network quantum field theory must satisfy this, this condition on the power spectrum. And for any translation invariant neural network Gaussian process quantum field theory, a Gaussian NNQFT, this condition is sufficient for reflection positivity of all of the correlators, because all of the correlators are just determined by the 2-point function. And there's a sufficient condition for solving this that arises in certain concrete examples. If this rho, which is a particular Fourier transform of the power spectrum, if this rho takes a particular form, then reflection positivity is guaranteed. Okay, so all of this is just like theoretical setup for a couple of examples that I want to mention, and then I'll conclude. So I want to give you specific examples of 2 specific examples of Gaussian neural network quantum field theories. And I'll give you another example of an interesting case that exhibits large N duality that actually doesn't satisfy reflection positivity. So in this family of examples, what I have so far with an overall setup is that I'm forming fields out of neurons in this way. I'm allowing the H to be constructed out of these Euclidean invariant Ls by prepending those Ls to some potential deep network Gij, and then I'm taking a linear output layer to form the fields. It turns out that H inherits the Euclidean symmetry of the Ls if a particular parameter constraint is satisfied. But and the Ls I chose in this particular example took this form. So what I want to do is specify 2 single layer models, in which case this Gij is just the identity function. And in this case, this scalar field is just of this form sum over ai li of x. And to fully specify a theory in this construct, in this family of examples, all you need to do is choose the parameter distributions for the b's and also this function f. And the reason why I present it in this degree of generality is because this f is useful. So when remembering that the field correlators are determined by the neuron correlators, the choice of this f and also the parameter distribution allows me to tune the power spectrum so that I can get different sorts of 2-point functions, which could be useful in many different contexts. Note in these cases, these neuron correlators are manifestly translation invariant. So in particular, in the 4-point function, I see this combination plus plus minus minus, which is this combination, which is invariant under translations. And SOD invariance follows for appropriately chosen Fs and Ps. So a specific example is that if we take F to be of this form and P to be a uniform distribution on the D sphere, then the power spectrum is this, which after an appropriate wave function or normalization, this is the free scalar field theory. Okay. So of course, this is a theory that satisfies reflection positivity. Another case is if you choose the Fs and the Ps this way, you end up with a power spectrum of this form, which looks like a free scalar field theory, except that you have this M up top. So this is a Cauchy distribution, and in the n goes to infinity limit, you get a Gaussian theory. This theory is reflection positive, and you can check that by studying this row. And finally, my last example is 2 examples. One architecture that we call cosine network, which is of this form. It has a cosine activation. Another one that we call GaussNet, which has an exponential activation. Something that's interesting about this setup is that the power spectrum the power spectrum is identical for these 2 architectures. It's both Gaussian power spectrums. I emphasize that Gaussian theories do not necessarily have to have Gaussian power spectrums, but this one happens to. And what that means is that these 2 different architectures with different activations give rise to dual theories in the infinite limit. However, at finite n, these theories have different symmetries and therefore different statistics. And in the extra slides, I have exact results for the connected 4-point functions just to demonstrate the point if you're interested. So it's interesting to think about classical configurations and symmetry breaking, spontaneous symmetry breaking in this context, but I'm surely out of time, and I am. So let me just summarize and provide some outlook. The basic setup is that we form fields out of neurons in this way. The fields have a different origin of randomness. It's from the neuron construction, not the distribution that arises in the path integral. So in particular, this is generally a non-Lagrangian setup to field theory. And to the extent that you can evaluate those parameter space correlators, it's non-perturbative. If you get clever enough to try to engineer architectures that induce field theories that satisfy the Osterwalder-Schrader axioms, then you get a Lorentz invariant unitary theory. And in particular, interactions because the free theories arise due to the central limit theorem, interactions come from breaking the assumptions of the central limit theorem by taking finite n or breaking the independence of the neurons. And here's an important direction for future work, a full theory of reflection positive neural networks. So predictions. This is a setup where Gaussianity arises due to a central limit theorem. So for theories built out of many nearly independent neurons, you should expect to see Gaussian theories. Something that I have some results on, but I didn't put in my paper, is it's interesting to study mixed field neuron correlators. And there's interesting things to say there. A potential use case is lattice field theory, and I'm happy to comment on that. But in the interest of time, let me just say thank you, and sorry that I went a minute over my allotted time. Thanks.
Well, thank you very much, Jim, for another great talk. Eva, you have a question there.
Sorry, I'll just continue my tradition of asking dumb questions. So I want to make sure that thanks for the really interesting talk. I want to make sure I understand the role of this large N. So, you know, it certainly sounds very sensible that you get Gaussianity in a limit where you get the central limit theorem. But what I'm trying to do is connect this back to, you know, dumb old perturbative quantum field theory using the usual Fourier modes as the basis, the usual Fock space and all of that. So in that context, the basis functions would be Fourier modes, and we still have the possibility of a Gaussian theory at finite n if we just do a cutoff, say of a scalar field theory, a UV cutoff. That is, it can be, you know, Gaussian at finite n. Yeah, I mean, I understand that you're aiming for the more rich and interesting case of interacting theories that are not based on a Fock space, you know, perturbation expansion. If I did that case, you would get Gaussianity for a rather different reason, if I understand correctly.
Right. So maybe I should comment. So this general result at the beginning really requires very few assumptions. I'm sorry, here it is. Yeah, so at finite n, there are just contributions to the connected 4-point function of this form. And so in your case, if you have a finite n Fock space construction, I mean, I guess the question that I would ask there is, what is it about that particular setup where these contributions are vanishing? And
right. Okay, so your answer is basically that I mean, I'm just talking about standard textbook chapter 1 of Peskin and Schroeder, you know, you can have a UV cutoff on the momenta. Let's just do scalars, so there's no issues with gauge invariance or anything. And you know, it remains Gaussian. So I guess what your answer is, okay, this formula would generically be non-trivial, but in that case, it will be 0. Is that?
That's right. That's right. And I should perhaps point out that the theories that I took at the very end had a very similar look to what we normally do with mode expansions in field theory. So in particular, I took this case. I'm sorry, I'm jumping around on my slides so much here, where indeed this is some sort of cosine. Something that I would point out relative to the normal mode expansion is, first of all, this could be prepended to a deep network, in which case there's some very non-trivial transformation that's happening. But the second is indeed that I am getting non-Gaussianities generally in this sort of setup. So I think in the particular sort of example that you're considering with a finite momentum space cutoff for the usual setup, it would correspond to assigning some particular statistics to the A of K's, if you would like, right? And that particular statistics would give rise to vanishing correlators. But the general formula, making very, very few assumptions, is of this form. I'm sorry I jumped around so much. So indeed, so in that case, this will vanish for some other reason. Generally, this sort of contribution is non-zero. And this is something you can find numerous places in the literature.
Okay, great. Thank you.
Wonderful. Thank you very much again, Jim, for a really fascinating talk. We have a half-hour tea break, coffee break, whatever time you're at, whatever time zone you're in, built in now. So we will